In this lesson, we're going to do a summary of curve sketching. So we have guidelines for sketching a curve, and I'm going to go through them. The first one is domain. So to determine the domain of D, then you're going to look at the set of values of x for which f of x is defined. Next, you have intercepts. To find your y-intercept, you're going to set x equal to 0 and then simplify. To find your x-intercepts, you're going to set y equal to 0 and then you solve for x. To check for symmetry, we can do f of negative x and simplify it, and then if we get out the original function, that means the graph is an even function and the graph has symmetry across the y-axis. If you plug in negative x for f and you simplify it and you get negative f of x, so it's the exact opposite of the original function, then the graph is an odd function and you have symmetry about the origin. And then finally, the function may be periodic. If you do f of x plus p and you simplify and you get out the original function, then the graph is a periodic function and the graph has translation symmetry. Next, we have asymptotes. For horizontal asymptotes, the line y equals L is a horizontal asymptote if when you take the limit as x goes to positive or negative infinity of f of x and you get out the value L. If that's the case, then y equals L is going to be the horizontal asymptote. If you specifically have a rational function, you can use this process from your previous math class. The degree of the numerator would be p, the degree of the denominator is q, the leading coefficient of the numerator is going to be a, and the leading coefficient of the denominator is b. To find your horizontal asymptote, you can use this chart. So for these values, if p is less than q, then the horizontal asymptote is y equals 0. If p equals q, then the horizontal asymptote is y equals a divided by b. And if p is greater than q, then there is no horizontal asymptote, but I have an asterisk that we're going to look at down here. For vertical asymptotes, we have the line x equals a is called a vertical asymptote if at least one of the following statements is true. So if you're taking the limit as x approaches a from the right of the function and you go to infinity, or from the left and you also go to infinity, and you also have as x approaches a from the right of the function goes to negative infinity, or from the left goes to negative infinity. If any of these are true statements, then you have a vertical asymptote at x equals a. For rational functions, to find your vertical asymptotes, you can factor and cancel any common factors and then set the denominator equal to 0 and solve. And then finally, slant asymptotes. So I'm going to go back up here. If p is greater than q, you have no horizontal asymptotes. But if p is exactly one more than q, so like p is 3 and q is 2, then you do have a slant asymptote, and to find it, you use long division, but you disregard the remainder. Next, we have intervals of increase or decrease. F is increasing when f prime is positive. F is decreasing when f prime is negative. To determine your intervals of increase and decrease, you can use the increasing-decreasing test. What you do is you compute f prime of x, then you find your critical numbers. To find your critical numbers, which we use the letter c to denote, you're checking whether f prime of c is equal to 0 or f prime of c doesn't exist. Once you find your critical numbers, you plot them on a number line and you create a sign chart for f prime. So again, you're picking numbers in between the critical numbers, you plug them into f prime, and that will determine whether f is increasing or decreasing depending on whether f prime is positive or negative. For local max and min values, we have our first derivative test and the second derivative test. For the first derivative test, your local max occurs for f, where f prime changes from positive to negative. For local minimum on f, that would be where f prime changes from negative to positive. For the second derivative test, we take the first derivative, set it equal, and solve, and once we find those values, we plug them into the second derivative. If the second derivative is negative, then the graph is concave down, indicating that we have a local max on f. For a local minimum, you take the first derivative, set it equal to 0, and solve. Those values you get, you plug them into the second derivative. If the second derivative is positive, that means that f is concave up, indicating that f has a local minimum at that value c. And finally, we have concavity and points of inflection. You find the second derivative, and then you set that equal to 0, and then also check where it doesn't exist. Then you create a sign chart, and f is concave up when the second derivative is positive, f is concave down where the second derivative is negative. And finally, your points of inflection on f are going to occur where f changes from concave up to concave down or vice versa. For this example, we're going to use the guidelines that we just covered, A through G, to sketch the graph of this function. So we're going to start by finding the domain of f. So we're going to take the denominator, set it equal to 0. I factored x squared minus 1 using a difference of squares to x plus 1 times x minus 1. So we get x equals negative 1 or 1. So our domain is x such that x doesn't equal plus or minus 1. To find the y-intercept, we're going to plug in 0 for x. And when we simplify, we get 0. So our y-intercept is the point 0, 0. To find our x-intercept, we're going to plug 0 for y. So here we have a proportion, so I'm going to put this over 1 and cross multiply, and you get x equals 0. So our only x-intercept is 0, 0. For part C, we're going to check if this function is even or odd. So we plug in negative x into the function, and when we simplify, we have negative x quantity squared, so this makes positive x squared. And then same thing right here, this is going to make positive x squared minus 1. And you can see that this is equal to the original function. Therefore, f is an even function and has y-axis symmetry. Next, we're going to check horizontal asymptotes. This is a rational function, so p is 2, q is 2. Because p equals q, according to the chart, that means that the horizontal asymptote is going to be y equals a over b. A is the leading coefficient of the numerator, b is the leading coefficient of the denominator, so that would be 2 over 1, or y equals 2. To find our vertical asymptotes, we can look at the denominators, so we can go x squared minus 1 equals 0, and again, when you solve this, you get x equals plus or minus 1. So those are our vertical asymptotes. Next, we're going to do intervals of increasing and decreasing, so that means we're going to take the first derivative, and that's going to require the quotient rule. So we go low, and then d high, minus high, and then d low, all over low squared. I'm going to distribute and multiply. So we end up getting negative 4x over the quantity x squared minus 1 squared. To find our critical numbers, first we're going to check where the derivative doesn't exist. So that's going to be x equals negative 1 and positive 1. And then we're also going to take this and set it equal to 0 and solve. It's a proportion, so we're going to cross multiply. And we also get that x equals 0. So we put these on a number line for f prime, and we're going to test numbers around these critical numbers. And again, we're plugging these values in for f prime to see if f prime is positive or negative on these intervals. So when we plug negative 2 in for x, up here that's going to make positive 8, and because this denominator is squared, that'll always be positive, so this will be positive. Same thing, if we plug negative 1/2 in here, the denominator will always be positive, and then if we plug negative 1/2 here, that'll make a positive. If we plug 1/2 up here, that'll make this negative, and a negative divided by a positive is negative. Similarly, when we plug in 2 right here, you get negative 8 over a positive is negative. So we get that f is increasing from negative infinity to negative 1 and also from negative 1 to 0. And we get that f is decreasing from 0 to 1 and also from 1 to infinity. Next, we're going to look at local max and min values on f. And if we go back here to the sign chart, we have at 0, f prime changes from positive to negative. Therefore, f is going to have a relative max at 0. And I just wrote that out. F prime changes from positive to negative at x equals 0. Therefore, f has a local maximum at 0. And then to find our actual maximum value, we're going to take 0 and plug it into the original equation. So the maximum value for f is 0. And again, make sure when you're listing a maximum or a minimum value that you just list it as a y value. Don't list it as an ordered pair. And for part G, we're going to look at concavity and inflection points. So I rewrote f prime for reference. We're going to take the second derivative using the quotient rule. So low and then d high minus high and then d low. And again, to take the derivative of the denominator, you're using the chain rule. So you bring the 2 to the front, you leave the inside the same, you subtract 1 from the exponent, then you times by the derivative of the inside. And it's all over the low squared. Okay, so I took this negative 4 and just wrote it in the front, and then over here, these become positive, and then I multiplied 4 times 2 times 2 to get 16, and then x times x is x squared, and then drop this down. Before I go on, if you'll notice, these terms both have the quantity x squared minus 1 in them, so if we wanted, we could factor the x squared minus 1 to the front, and again, let's make sure I did that right. So I factored this out, and you're left with negative 4 and then 1 of them. And then when you factor this out over here, you're just left with the 16x squared. And we can do that because now this cancels with one of these. So when I distribute here, we get negative 4x squared plus 4. So negative 4x squared plus 16x squared is going to be 12x squared. And then we have plus 4 all over the quantity x squared minus 1 to the third power. All right, so we're looking for concavity and inflection points. So first we want to check where this doesn't exist, and this doesn't exist at 1 and negative 1. Okay, so I wrote that out here, and then we take the second derivative and set equal to 0 and solve. So when you cross multiply, you get 12x squared plus 4 equals 0, and there's not going to be an x value that you plug in and square, and then you'll get this to be negative 4. So that it equals 0. So therefore, this does not produce any critical values. So I'm going to set up these guys on a number line for f double prime. When we take negative 2 and plug it in right here, you get 4. 4 minus 1 is 3. 3 cubed is going to be positive. When you take -2 and plug it in here, you also get a positive, so this is going to be positive. When we take 0 and plug it in here, you get 0, so that's gone. When you plug in 0 here, you get -1 cubed, which is negative, so then the fraction will be negative. When we plug in 2 right here, you get a positive. When you plug in 2 here, you get 4 minus 1, and so that's also going to be positive. So f is concave up from -infinity to 1, and then also from 1 to infinity, and therefore f is concave down right in this interval from -1 to 1. To find an inflection point, you would take -1 and 1 and plug them into the original equation. However, you can't plug -1 or 1 into the original equation because it's not in the domain. So there's no inflection point. So I drew the vertical asymptotes at -1 and 1, the horizontal asymptote at 2. So I chose an x value to the left of this vertical asymptote. I chose a value in between these two vertical asymptotes, and then I chose a value over here, plugged them into our function, and got these points. So this first point is -2 up 2 1/3. This point right here is over 1/2 and down 2/3, and this last point is the same height. The graph had y-axis symmetry, so that means that we can curve this down and then do the same over here. And then by nature of a rational function, coast along the asymptote on both sides. So there's our final graph. All right, guys, thanks for watching.